Thank you. Hello, everybody. Thank you for joining today. The title for my presentation today is Forward Chaining and Self-Embedding Watermarking for Tamper Detection in a Continuous Stream of Data. So let's get a brief idea about data security and information hiding and security. So typically data security has information hiding, information security, authentication, tamper. Typically we divide this type of security in different techniques. We have cryptography, steganography, and watermarking. In cryptography, as we all know, we have a plain text. It gets encrypted into a ciphertext, and then the ciphertext gets decrypted into a plain text back again. Watermarking, as you can see on the image, right, this is an image of the Hollywood Capitol records in Hollywood, and this image is taken by iStock, and the iStock have their watermarking on the entire image, so they've watermarked it, and so that's a watermarking. And then steganography. Steganography is something like how if on this very specific building in Hollywood, right there on the top, there is a red light that's glowing. And that red light that's glowing, that is glowing in Morse code, which is actually saying Hollywood. So that's like a steganography type of encryption or information sending, which is hidden into the data, but it's not visible to everybody, but it's actually used to send the data. So that being said, let's get a brief idea about digital watermarking. So digital watermarking is basically hiding any sort of patent information or metadata or any sort of data within a digital throughput. So we have a data that's being transferred from various nodes, or we have data transferring from one point to the other point, and hiding a metadata or hiding a patent information within the data is digital watermarking. So on the right side, we could see that the information hiding is typically, as I mentioned earlier, is divided into cryptography, watermarking, and steganography. And so in watermarking, it's divided into two techniques. We have fragile and we have robust watermarking. And depending upon different applications, whether it's being tamper detection or authentication or copyright protection, fingerprinting, copy prevention, we can easily use fragile watermarking or robust watermarking. Now, in fragile watermarking, on the left side that you can see, if the watermark is destroyed with slightest manipulation, that's fragile watermarking. But if a watermarking cannot be manipulated or cannot be modified, that's robust watermarking. So depending upon the applications, we can use different techniques of watermarking. There's also something called semi-fragile watermarking, private and public watermarking. And similarly, once a data is watermarked, we have different techniques for extraction. And on the table below, you could see that depending on if we're using the original data for watermarking, then it's a non-blind extraction. If we're using the original watermark and the key and the watermark data, then it's a semi-blind extraction. But if we're only using the key and the watermark data for extraction, then that's a blind extraction. So we have different techniques for extractions as well. Now, there are some requirements and properties for digital watermarking. So something like these digital watermarking needs to be robust. It needs to have a certain level of security. It has to have a computational power, and it also needs to be imperceptible. Now, we know that cryptography typically uses a heavy computing power. There's a lot of algorithm that's running behind the scene. There's a lot of computation that's happening behind the scene. So ideally, we want something that's very lightweight, specifically in environments such as IoT or cyber physical systems, wireless sensor networks. We want something that's lightweight, less computative, but also strong, secure, and imperceptible. So that's why we're routing to digital watermarking, because it's lightweight. It doesn't require so much of computing. It's faster. At the same time, it can be easily implemented in various applications of IoT or cyber physical systems or electrical vehicles as of speaking right now. So moving ahead, there are a few things that we want to get familiar with in terms of this approach. We have something called false positive, where let's say if we have a stream of data, input of data, and if the data is not modified, but somehow there's a detection of a tamper at the end of the receiving end, we call that a false positive. Then we have something called false negative, where if the data is modified in the throughput, or if the data is modified from while transferring from one node to the other node, but there is no tamper detection, and that's called false negative. We've used something called a synchronization point over here. So as the data are flowing in, or as the data are, because there's a continuous stream of data, we want to divide those data into packets or group. And we use a technique for synchronization point, which is a mod operating function. And depending on that mod operating function, these data elements are clubbed together or grouped together in one group, and then they are sent together in a packet. So that's synchronization point. It's a very important point for this research or previous research based on this technique. So that's synchronization point. Then we have forward chaining and backward chaining. So if we assume, let's say the center data group is the current group that we're working with, and the incoming data, which is the next data that's coming in the pipeline, if we use that data and the current data, and we watermark them, and after, we encrypt them, and after encrypting, we watermark that data into the current group set of data, that's called forward chaining, where we're using the data that's coming in next. Whereas in the pipeline, if we are at the current data and there's data that's already been sent to the receiver, if we use those data and the current data, and then we form a watermark, and then we watermark into the current group, that's called backward chaining. So there's forward chaining and backward chaining. There are a lot of works done in the past. Dr. Guo, my advisor, she was one of the first person to, she presented one of the first papers where they developed this chaining method or chaining technique, where they used a group of data. Each data elements were hashed, and then the group of element was hashed, and then the next group and the previous group, they were also hashed together, and then a watermark was created, and that watermark was embedded into the current group. But then further down, few years down the line, Ibrahim Kamil and Hussein Juma, they created a simplified version of the same technique, where they did not cryptographically hash each data elements. They just took the groups together, and then they created a hash, create a watermarking system, embed the watermark into the current group, and moved along. And then the further refinement was done by them again, where they added a serial number and a delimiter to segregate each groups, and each groups could be identified. And then in further few years down the line, there was a dual chaining watermarking scheme that was developed, where they were dividing the current group into two groups, and then they were creating two watermarks, and then inserting the watermarks into the current group. Now, the major problem with most of these techniques they had a lot of false positive and false negative results where, a data may not have been tampered, but it still shows at the end, at the receiving end, that it's tampered, or if data it's tampered, but then it doesn't show at the receiving end that it's not tampered, or scalability issue, because some of these functions, some of these techniques are are hashed so much that it gets high, it has a high computing power. I mean, it requires a high computing power. So there's a scalability issue. It requires a lot of time to compute. So there are a few issues with these techniques, and that was the major motivation to move along with this research. So what in this current research, what we propose is a forward chaining with self-embedding of the watermark. And I can provide you a brief example. So let's say if we are currently using group GI, where group GI is composed of, and for argument's sake, it's about 7 data elements. So each of these data elements have to be integers. Well, we've used integers for this research, but then, with minor modifications, this could extensively used with some other data sets also. So let's talk about the first 3 data sets. So the first data set, for example, is 9877. Now, in this technique, what we've done is that we've ignored the last 2 bits of each data elements. And so, for example, 9877, after ignoring the last 2 bits, becomes 9876. 9751, which is the next in the group, once we ignore the least 2 bit data, once we ignore the least 2 data bits, it becomes 9748. Similarly, 9223 becomes 9220. Now, so once we've ignored the least 2 bits, we group them together, we concatenate each of these data elements with the key, and we hash it. Now, once it goes through a hash function, we transform the hash output into binary. And so, for example, just again, for the argument's sake, if let's say the hash 2 value that you see in the screen is 1, 2, 3, A, B, C, D, and converting them into a binary format, we have 0, 0, 0, 1, 0, 0, 1, and further along. So what we do is that we take each bit of the hashed value, and then we insert in the second position from the right, which is the second position from the right. That's where we insert the hash 2 values. And then the hash value comes where we have the group element GI and then GI plus 1, which is the next coming in the pipeline. We take those 2 groups, we concatenate that with the key, and let's say we get a hash value A23BCD, and converting them into binary, we get a binary number. We use the binary bits 1, 0, 1, and then we insert in the last bit of the numbers. So once we insert these 2 bits into the numbers, this number going back to decimal format becomes 9877, 9748, 9221. So this is a technique how we've done a forward chaining and self-embedding both into a set of groups. So you see how so after embedding the watermark, 9877 remains 9877 after the watermark, but then 9751 becomes 9748, and then 9223 becomes 9221 after the watermarking. After the watermarking is done. So that's the technique that we've used in this approach. Now, as far as the extraction is concerned, it's the same process going back in reverse. Let's say in the pipeline, the data that are coming in, we have 9777, 9748, and 9221. We would do the same thing. We would go back in reverse. The first step would be, we would bifurcate. We would ignore the least two bits of the data elements, and we would get these values, and then we would take those ignored last two bit, and then we would form back our two watermarks. The second bits become watermark 2. The last bit from the right becomes watermark 1. And these are the two watermarks which are key for our matching what we've got and what we've extracted into the incoming data set. So you could see now, what you could see is that once we take these ignored data, the ignored data elements, the least two bit data elements that's been ignored, we group them together just like previous times. We add a key and then we hash it. And then the incoming group, again, that's coming into the pipeline, we do the same process. We group them together, we concatenate that with the key, and then we hash it. And at this point of time, the hash values that we get, which is 0001 ... and then 101000, and then further along. This two values is then matched with what we've extracted from the incoming data, which is watermark 1, and watermark 2. Once we match this, depending upon whether this has been matched or not, whether it has been tampered or not tampered, we come up with various scenarios. We can figure out whether the current group data has been tampered or not. If there's a group of data that's coming in that's been tampered or not. If there's a previous group of data that's already has been sent out that's been tampered or not. We can find out different things with just a simple approach. There's a couple of things that we need to know before we get into verification of the watermark. The first thing is that there's two types of watermarks, as I stated in my previous slide. There's a primary watermark, which we can call it as an integrity watermark, which is formed by grouping two group of elements together with the key and creating a watermark from joining the two groups. So that's because it's joining the two groups, it's creating an integrity between the two groups. And then the second watermark is WM2, which is secondary watermark, or the modifying watermark, which is, this is the watermark that's been created from the current group itself. And this is also known as modifying watermark because it's using the current group. If there's any modification in the current group, or there's any tampering in the current group, this WM2, this watermark will get modified, or this will get distorted, or we can find that out from watermark 2. There's two types of verification. There's a preliminary verification and a final verification. The preliminary verification is done with using the watermark 1, which is from the current group and the incoming group, or the next group that's coming in. Once we use the watermark by those two groups, and then we verify, that's our preliminary verification. And then final verification takes place where we use the preliminary verification of the current group with the next group, and then the final verification with the previous group and the current group, the watermark from the previous and the current group. So we use that watermark from the previous and the current, and also we use the preliminary verification of the current and the next group. And we use that together to do a final verification. With just these two verifications, there comes in various scenarios that I'm going to talk in my next slide. So we could see that, let's assume that we are right here in the current group, which is group 2 or G2. And if the data set that's incoming, and that data set is, we get the data set, we extract our watermark, and once we extract the watermark, we compute the watermark from the least significant bit ignored data groups. So we match them. If they all come true, then we know that the current group is good. There has been no modification, or there has been no tampering the current group, because both the verification came out to be true. P1, PV1 and V1, they both were true. So that's good. But what happens when there's the watermark does not matches? That is, when the preliminary verification and the final verification, they both come out false, what happens then? And at that point of time, that's when we use the watermark 2, which is WM2, to verify whether the current group, which is the group in question, if that's been modified or not. And at that point of time, it just turns out that when we're working with the current group, we're only caring about the current group, because each group, as they come in through the network, or it comes through the packets, they get individually verified, and the group in the question is the current group. So if the watermark 2 is false, then it turns out that the current group G2 is modified. But if that's not false, if it's true, that just means that, you know, there are groups that's either coming in, or the data set that's coming in, or the data set that's already been gone through the node, that's been modified. But the current group that's in the node right now, that's perfectly unmodified, has not been tampered. And then same thing. So if it's also if we have the previous group where the final verification was true, then depending upon false and true, the current group probably be modified, and it's not modified if the watermark 2 is true. But then if the previous group final verification is false, at that point of time, we'll still use the modifying watermark and find out if it's true or false. If it's false, again, then that's eminent that, you know, the current group has been modified. But if the watermark 2 is true, that means that either there is some group of data or packet of data that's missing between the current group and the next group, or the previous group and the next group that has been modified somehow, and that's why we're getting our watermark 1 to be false. So again, watermark 1, it's an integrating watermarking system where, you know, we have the current group and we have the next group and the previous group. They are linked together, so it kind of integrates the group set and finds out whether if there's been modification made in each of these groups, the previous, the current, and the next. But then the watermark 2 is where it finds out whether the current group in question, whether that has been modified or not. So moving along, there's a couple of things that I really want to point out, which is a flaw in this approach, is that, let's say, well, I've already introduced WM1 and WM2, which is the primary and secondary watermark. So let's say if I take a number 9726 and I go through the process of, you know, ignoring the least 2 bit and then creating a hash function, passing it through a hash function, getting the watermarks, we could see that because we're ignoring the least 2 bits of the data element, so a hash function of 9724, 9725, 9726, and 9727, the hash functions of these numbers will result in the same output of a hash function. So that is, it gets tricky at that point of time. So any modification made in the least 2 bit of a data element would remain unnoticed and will not be detected. So this approach is sensitive when it comes to modifying the last 2 bit of the numbers of a data element. The second thing is false negative. So let's assume, again, we have a group of data that's being sent from the sender, right? And so we have this group which is a group of 5 elements for an argument's sake. We concatenate them with a key. After ignoring the least 2 bit, we go through a hash function. We get an output something like 7468 ... And the 74, once it gets converted to binary, the result output is 01110. Now, after the watermark is embedded into the current data set and it's sent to the node, let's say an attacker decides to attack the first data element 97, 57 and change it to 97, 61, is the same thing that's happening that I explained in the previous slide. Once the first data element gets modified and is sent through the node, we get we get this group of data elements that starts with 97, 61, which is already been modified. We go through the same process, concatenate the data set, add a key, concatenate that, go through a hash function. You would see that the hash value 75, the binary value for 75 is also 0, 1, 1, 1, 0. So both of these hash functions have the same binary, and that can create a confusion, and that could also create false negatives. So depending upon how large is your group of data, this can get implemented into this false negative can get implemented into the group of data that will not get detected. So that's also something to keep in mind. And so once this approach was implemented, we tried to make different attacks. What we did is we modified a data element into the group. We deleted a data element within a group. We made insert a data element within a group. And then we also did something called a burst attack, where we have multiple of data at random times. They were being inserted, deleted, modified at the same time. So we did these two types of attacks. So now when it comes to results, when we did a single attack, we find out that using this approach, right, the false results, which is the false negative and false positive results, it tends to 0 once the group size becomes larger. So as I was showing in the previous group, in that example, the group set was about 5 elements, and it was giving us a false negative result. But if that group size becomes larger than 10, 12, it becomes larger than 12 at that point of time, for a continuous stream of data, there would not be any false negative. There would not be any false positive, false negative. You can see in this graph how it converges down to 0. So that's one observation we found. The second observation was that we did a forward embedding and backward embedding. The forward embedding was using the hash value with the bits starting from the left-hand side, and the backward embedding from the right-hand side of the hash values. And we embedded that into the watermarking scheme and saw the results. And it turns out that regardless of that being forward and backward embedding, and regardless of the hash functions, which is MD5 and SHA-256 that we've used, there seems to be a similar trend at a group size of more than 10, 12, the false negative and false positive results tends to be 0, which basically means that if a group size has more than 12, any tampering that is done will be detected, and there will not be any false positive, false negative. Moving forward, we did a scalability test where we increased the data size and the range of a data set. So we increased the data size to about 100,000, and we tried to find out how long does it take to create a watermark, insert and extract, and we see that it's linearly increasing as the data sets increases. And as far as the group range is concerned, as we were increasing the group range, for small groups, we had high false positive and false negative. For larger groups, it tends to be 0. So it's showing that as the group size is larger, at least 12, we see a better results when it comes to false negative and false positive. And then finally, the burst attack, where we did an attack within the group at random times. And you could see because of the random times, we would probably need a larger group size. In the previous slides, it was coming out to be a minimum of 12 data elements within the group. But at random times, you could see that it now has been expanded, increased to 14. So on a safe side, let's say if we go with the group size of at least a minimum of 15, which is being the lower bound, it's safe to say that any attacks that will perform will be detected, and no attacks will get undetected. And so in conclusion, this approach has been very successful in reducing the false positive results compared to what they've done in the previous times. The technique is linearly scalable with larger data sets, larger group size, the time increases linearly, there's no exponential increase. And with the minimum threshold of a group size, all the data, if gets modified or tampered, will be successfully detected. And with that, I conclude my presentation. If there's any questions, I'm welcome.